paragraph. Doing work. Under the brackets, I can write down that is, comma, of exerting a force over a distance. That is, of exerting a force over a distance. Close the bracket. But not all of them are equally relevant to chemistry. But not all of them are equally relevant to chemistry. So if you can't hear or if you can't see the screen, please let me know through the chat box. Okay, and for the next paragraph, for the next point, you can write down the energy contained in tidal waves. The energy contained in tidal waves for example, can be harnessed to perform useful work. Can be harnessed to perform useful work. But the relationship between tidal waves and chemistry is minimal. And chemistry is minimum or minimal. For the next paragraph, you can write down, in that case, work is defined as directed energy change resulting from a process. Under that, you can take another point as a subtopic. So under the next topic, you can, that should be subtopic to that point. Write down the kinematic energy or kinetic energy. I will write down that one for you. Kinetic energy. So under the kinetic energy, you can write down the energy produced by a moving object. The energy produced by a moving object. The energy produced by a moving object. So actually tidal waves have the kinematic energy, right? So for the next topic, for the next point, you can write down others include radiant energy. Others include radiant energy, thermal energy, chemical energy, and potential energy. Okay. For the next topic, for the next subtopic, you can write down radiant energy. You can write down radiant energy. So under the radiant energy, you can write down in the bracket first. You can write down as solar energy, and close the bracket. Comes from the sun. Comes from the sun. Comes from the sun, and is Earth's primary energy source. And is Earth's primary energy source. For the same paragraph, you can write down Solar energy heats the atmosphere. Solar energy heats the atmosphere and Earth's surface. Earth's surface. Comma stimulates 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 growth of
Sir, can you repeat the sentence?
growth of vegetation stimulates the growth of vegetation through the process known as photosynthesis. I'll write down that for you. Okay, I'm going to repeat that one. Radiant energy or solar energy comes from the sun and is Earth's primary energy source. Solar energy heats the atmosphere and Earth's surface stimulates the growth of vegetation through the process known as photosynthesis. And influences global climate pattern. So the whole paragraph is like this. I'm going to repeat that again. Radiant energy or solar energy comes from the sun and is Earth's primary energy source. Solar energy heats the atmosphere and Earth's surface, stimulates the growth of vegetation through the process known as photosynthesis, and influences global climate patterns. And influence global climate patterns. And next, under the next topic, you can write down thermal energy. The second one is Thermal energy. Under the thermal energy, you can write down thermal energy is the energy. Thermal energy is the energy associated with random motion of atoms, random motion of atoms, random motion of atoms and molecules. And molecules. Right, I think you heard me properly. Thermal energy is the energy associated with random motion of atoms and molecules. And for the next point, you can write down thermal energy can be calculated from temperature measurements. Calculated from temperature measurements. Calculated from temperature measurements. And for the same paragraph, you can write down the more vigorous the motion, the more vigorous the motion of the atoms, the more vigorous the motion of atoms and molecules in a sample of matter So I'm going to repeat the same thing again. So sorry for the disturbance today. I think there are lots of lectures going on, so I think you can probably hear me. So if you can't hear me, please let me know. It is make sure you have a comfortable hearing with this lecture. So otherwise it's going to be a boring one, So I'm going to again repeat the one. Thermal energy is the energy associated with the random motion of atoms and molecules. In general, or the thermal energy can be calculated from temperature measurements. Thermal energy can be calculated from temperature measurements. And for the same paragraph, the more vigorous the motion of the atoms and molecules in a sample of matter, atoms and molecules in a sample of matter, comma, the hotter the sample is, and the greater its and the greater its thermal energy, and the greater its thermal energy. So for the next point, however, again for the next point, so however, however, we need to distinguish carefully between thermal energy and temperature. However, we need to distinguish carefully between thermal energy and temperature. Then you can write down as an example. Then you can write down it as an example. A cup of coffee at 70 degrees. A cup of coffee at 70 degrees. You know how to write down 70 degrees? I mean, 70 degrees. Has a higher temperature than has a higher temperature than a bathtub filled with warm water at 40 degrees. So let's talk about the differences here. So you have a bathtub filled with, you don't need to write down this one, bathtub filled with warm water at 40 Celsius. And at the same time you have what? A cup of coffee of 70 degrees. You have a cup of coffee at 70 degrees. So which one has a higher temperature? Which one has the highest temperature if I ask? So just consider bathtub filled, warm water filled the bathtub at 40 Celsius. But a cup of coffee is a, it's a small amount in volume, right? This one has the most volume. The bathtub has the more volume. And if I ask what is the highest temperature in here, which one has the highest temperature here? It is indeed the cup of coffee. It is indeed the cup of coffee. So I'm going to write down the highest temperature. The highest temperature is how the highest temperature, which one is the one, just the cup of coffee. But in the same time, if I ask which one has the highest energy, which one has the highest energy included there? So in that case, what we are going to say? Is it a cup of coffee or the warm water filled the bathtub at 40 degrees? Yeah, it is the bathtub. So now you can see, now you can identify actually there is a difference between the heat and the temperature, right? So heat does not mean if we have the highest temperature, it doesn't mean we have the highest energy, right? That's the point here. Even though this one has the highest energy, it has a small energy. Energy-wise, it is small. So now we can distinguish this one and write down this one. So I think we feel, end up the paragraph like this, right? Then a bathtub filled with warm water at 40 degrees. Now put a comma, then you can write down, but much more thermal energy is stored, but much more thermal energy is stored in the bathtub water. In the bathtub water, in the bathtub water, because it has a much larger volume. Because it has a much larger volume. Because it has a much larger volume. And greater mass. And greater mass, right? And greater mass than the coffee, and therefore more water molecules and more molecular motion. More water molecules and more molecular motion. More water molecules and more molecular motion. So thermal energy කියලා කියන්නේ තාප ශක්තියට. So there's a difference between the temperature and the heat or the energy, and the difference is actually, it doesn't mean does not depend on the volume or anything like that, or the highest temperature which one has, but it depends on the mass actually, right? Mass and the volume, right? So what happened in here is, අපි දන්නවා මේ කෝපි කෝපය ගත්තොත් රත් වෙලා තියෙන ඒ වගේ එකක දැන් ජල අණු තියෙනවා. There are water atoms in the cup, right? So when we increase the temperature, අපි උෂ්ණත්වය කියලා කියන්නේ ඇත්තටම කිව්වොත් එහෙම දැන් කෝෆි එක උෂ්ණත්වය කියලා කියන්නේ ඇත්තටම when a cup of coffee has some larger temperature, what happened inside the cup in molecular level is that there are many atoms. Coffee also made up of atoms. So likewise, there are kind of atoms like this, right? There are free electrons outside these atoms as well. What happened is, if this cup of coffee has more energy, which means that the relative motion of these atoms have a higher speed. So let's you can consider this is my cup of coffee, these are my atoms. In this case, if it is now in this case, if it has like 0 Celsius, which means there are no relative motion. Okay, see, in 0 Celsius there are no relative motion, I see. But if we heat it up to 70 degrees, what happened is each of these molecules going to be relatively move each other. So they are going to be, I mean, ඒගොල්ලෝ ගොඩක් වේගෙන් චලනයට පටන් ගන්නවා අණු. Right? Atoms වේගෙන් චලනය වෙන්න පටන් ගන්නවා. They have a very high speed, and what happened is in the same time they are going to be collapsing with each other. They are going to be collapsed with each other. They are going to be collapsed with each other. So in that case, if you put a thermometer in here, you can identify the temperature has increased. At the same time, you know, if you put your hand so at the same time, if you put your hand inside this inside this 70 Celsius cup of coffee, what happened is it's going to be burned, right? What happened is to your fingers, to your tip of fingers, these molecules are going to, I mean, collide with your hand. So in that case, it has a great speed, but we cannot see it by our naked eye. So that's how actually the if I ask this question, what kind of energy is stored, or what is the type of energy that is in a moving object? What is the type of energy which is located in a moving object? Yes, so it is kinetic energy, right? So in that case, I can say that in case of higher temperature, or the temperature of any object means that it has a higher kinetic energy between its atoms. It has a higher kinetic energy in between the atoms. So in that case, let me ask you another question. So if I take a solid object, for example, if I take a wooden table, table made out of wood, you know, their atoms are packed. The atoms are packed in a more tight way, right? Not like a liquid. So in that case, there are no kinetic energy. There is no kinetic energy. That's why all these the woods and other stuff, the solid ones are stay in a constant temperature. But what happened with the any kind of a water? If we heat up the water, then so you have to remember that kinetic energy is depend on the, it increases when the temperature rises. So any object, the temperature actually means by the mean value of, or the average value of the kinetic energy of those particles. So I think it's enough with that. We can actually discuss these things in future things, but I want to get I want to introduce this subject for you. So next you can write down chemical energy. Next, you can write down chemical energy. Under the chemical energy, you can write down chemical energy is stored. Chemical energy is stored within the structural units of chemical substances. Within the structural units of chemical substances. For the next point, you can write down when substances participate in chemical reactions. When substances participate in chemical reactions. Chemical energy is released. Chemical energy is released, stored, or converted to other forms of energy. I'm going to repeat that one. Converted to other forms of energy. Chemical energy is stored within the structural units of chemical substances. Its quantity is determined by the type and arrangement of constituent atoms. Sorry, the second one I think you don't need to write down. So the next one, when substances participate in chemical reactions, chemical energy is released, stored, or converted to other forms of energy. So for example, actually you don't need to write down, you can hear about these things. I think how actually people's or the body of a person store energy. It is stored as a chemical energy in our body. For more specific ones, we store energy and the animals store energy as glycogen. Actually, it is a chemical energy. It falls into the category of chemical energy, and for the body of the person, they actually storing energy as chemical energy. So what happened is, if we work out, or if we climb a stair or something like this, climb a mountain or go for a hike, what happened is these chemical energies going to converted into kinetic energy. So in that case, we can move around, right? So because our body is also Is in a moving, I mean, if we move, this chemical stored chemical energy is converted into kinematic energy or the kinetic energy. And for the next one, the fourth one, for the fourth one, you can write down potential energy. Potential energy. For the fourth one, you can write down potential energy. For the potential energy part, you can write down potential energy is energy available by available by virtue of an object's position. Virtue of an object position. For example, you can write down, put example there, and you can write down. So I'm going to repeat the same thing that I have told earlier. Potential energy is energy available by virtue of an object's position. Virtue of an object's position. And as example, you can write down because of the altitude, because of the altitude, because of altitude, because of altitude, a rock at the top of a cliff, because of the altitude, a rock at the top of a cliff, has more potential energy, has more potential energy and will make a bigger splash and will make a bigger splash if it falls into the water. Into the water below. Into the water below than a similar rock. Below than a similar rock. Below than a similar rock. Below than a similar rock located. Below than a similar rock located partway down the cliff. partway down the cliff. So actually, when we talk about the potential energy, both chemical and potential energy, as a composite word, for both of them we say as both of them are known as the mechanical energies, the two major mechanical energies. So under the mechanical energies, actually we are talking about chemical energy and the potential energy. So chemical energy, sorry, not the chemical energy, it should be the kinematic energy, okay? It should be the kinetic energy. It should be kinetic energy and the potential energy known as the mechanical energies. To the two major mechanical energies, and so since the kinematic energy depend on the speed or the it actually known as the energy produced by the moving object, right? So if we walk in a way, so we have a kinetic energy, but potential energy depend on the altitude or the energy available by virtue of an object position. It depend on the virtue of an object's position. So if we talk about object position, so consider this pink line is my ground level. This one is my ground level. Consider this as my ground level. Usually when we refer to the potential energy, commonly we take ground level as our zeroth position, or here we say my energy denoted by capital E, potential energy denoted by capital E, subscript simple p. So this is here in the ground level, potential energy is equal to 0. Potential energy is 0. And if there is any object on a higher altitude, say if a person goes from the ground level to the first floor, so here he is going to produce the energy called, at this altitude he is going to have some potential energy. Let's say it is 100 joules. Okay. So it depends on the position. Okay. It depends on the position. So in here, again, I think you can understand this one. It depends on the position, right? So if we have a gas tank on our floor, let's say there's a gas tank on our floor. So if we take that gas tank and put it on top of a table, so there is a potential energy produced in this gas tank. But if this gas tank is not moving, right? It has zero velocity. We say in SFT, we say zero velocity, there is no motion. Okay. So in that case, there is no kinematic energy in this object, but we have potential energy. But if I consider this original position, it has no potential energy because it's on the ground floor. And since it is not moving, we also say there's no kinetic energy there as well. And likewise, if you move the object on the ground floor, then there's going to be kinematic energy produced in this object if it's going to move on. Right. Likewise, these are the simple things. And here in the examples, I say that altitude cliff, a rock at the top of the cliff has more potential energy, right? That's why if you throw a rock from a higher position, it's going to make a bigger splash, right? But if you throw a rock from here, it's going to be making a, no splash or something like that. That's because of the energy content is larger in a higher altitude. I think you can probably understand this one. So I'm going to move on to the next point. Before that, I want to show you an example of this conversion of energy. So I want to show you a minute. Let me stop the share for a moment. So I think you can see the figure in here. So what it says that this is the figure of a dam, right? It's a figure of a water dam. And so they say that as the water falls over the dam, its potential energy is converted to kinetic energy. Why we are building up dams is to convert this potential energy to kinematic energy. For which kinematic energy? As well, like what? Use of the energy to generate electricity using the turbines, right? We can, using this kinetic energy, we can rotate the turbines and we can produce electricity called as, specifically as hydrostatic hydroelectric power. So if you want a more detailed that kinematic energy and this potential energy conversion, the first I'm going to move a little bit on the theories. So in that case, I can come up to a better detailed version so you can understand some concept as well. I will explain this one again with the detail figure. At the same time, actually, this one is asked by for the exam, and It is actually very easy subject. You know, the chemistry. The chemistry part is actually very easy. This one. This is just about equating energies and getting formulating some equations. So it's very easy. And what's the problem is that we have to learn so many terms because this is a new subject. You know, actually, when we come to the thermodynamic, the main subject, it's kind of a, there are lots of terms. We don't open system, closed systems, likewise, and the system, the environment, the boundaries, work, heat, systems, and likewise there are lots of things, but it's kind of a common thing and you can understand things easily, so you don't need to worry about these things. And if I want to move on to the next point, it's about conversion of energies. So under that, first I want you to get another point, but not under the potential energy, which is a individual paragraph you can write down. All forms of energy can be converted. All forms of energy can be converted. All forms of energy can be converted. All forms of energy can be converted from one form to another. From one form to another. From one form to another. So I'm going to repeat that one because it is a golden rule in energy conservation. All forms of energy can be converted from one form to another. So there are lots of energy conversions here going on. And for example, you can write down, for examples, first point under the examples, we feel warm when we stand in sunlight. We feel warm when we stand in sunlight. Because radiant energy is converted because radiant energy radiant energy is converted to thermal energy on our skin. Radiant energy is converted to thermal energy on our skin. The second example, when we exercise, when we exercise, chemical energy is stored in our bodies is used to produce kinetic energy. Is used to produce kinetic energy. So I'm going to repeat that one. When we exercise, chemical energy stored in our bodies is used to produce kinetic energy. Next example, when a ball starts to roll downhill, when a ball starts to roll downhill, its potential energy is converted to kinetic energy. Again, I'm going to repeat the same thing as well. When a ball starts to roll downhill, its potential energy is converted to kinetic energy. Its potential energy is converted to kinetic energy. So, as for the second point, not an example, for the second point, you can write down: energy can be neither destroyed destroyed nor created. Energy can be neither destroyed nor created. So under that, you can write down on the brackets, open the brackets and write down: when one form of energy disappears, some other form of energy some other forms of energy of equal magnitude must appear. So the last paragraph under the nature of energy and types of energy, you can write down: the principle is summarized by, you can close the bracket, and this principle is summarized by the law of conservation of energy. I'll write down for you: the law of conservation of energy. Under that, you can write down using a colon: the total quality of energy the total quality of energy. Sorry, not the quality, it should be the quantity. The total quantity of energy in the universe, is assumed constant. Is assumed constant. The total quantity of energy in the universe is assumed constant. Now, okay. So before we go for a kind of a break, I want to explain this golden rule here. So the law of conservation of energy is the main thing we have to talk about under the thermochemistry, and there were some small questions asked by on the MCQ papers under the law of conservation of energy. Uh, so since you do not undergo any equations, but I would like you to try that question. Let me find out that question real quick. Okay, I think I found the question. Let me share the screen for you. Can you see the screen? I think you can, right? So this one is a 2020, the last year paper. So I want to make your attention on this question. It is okay if you got the question answer wrong, it's completely okay. So if you can see this ninth question, ninth MCQ, can you read down and can you find any answer and you can put it on the chat box? It's okay. If you don't know, it's okay as well. Just take a minute and give me an answer to the chat box. The ninth MCQ, okay? This one. Right. So, energy is changed in chemical reactions, right? For example, for simple chemical reaction, we already know we can say the reaction of natural gases or oils with oxygen or burning oxygen of fuels. What happen? There is going to be a energy change after this chemical reaction, right? In chemicals, like in fuels such as natural gas or oils, any kind of oil, uh, what kind of energy is stored in the natural gases or oils? I mean, petrol, diesel, and such stuff. What kind of energy they are storing? Is it potential energy? Is it kinetic energy? Is it thermal energy? Is it chemical energy? What kind of energy? You might think, I mean, actually, the same as our bodies, oils have stored energy as chemical energy. So what happened? We react the oils with oxygen. They are going to give thermal energy and the carbon dioxide, right? Carbon dioxide plus water vapors. So in a car, what happened? If we put petrol, that is chemical energy first. Then in the engine, what happened? Chemical energy is converted into thermal energy from the wheels or the tires of the vehicle. What happened? This this thermal energy is converted into kinematic energy to move the vehicle, right? To move the vehicle, the energy is going to be changed. So likewise, we know that after some chemical reactions, or most probably in every chemical reaction, the energies or the type of energies are going to be changed. Okay. So what are, if I talk, what are the results or the products of the chemical reaction of fuel with oxygen? If I go back to the whiteboard here, if I take this one, in chemical reactions, for example, take LP gas here. Let's take LP gas. Okay, in LP gas, the main component is called as propane. I am going to write that down. So the propane, we have CH3, so C3H8 is going to be react with oxygen. Then the product of this reaction is carbon dioxide plus H2O plus energy. So you can write down this one as well. This is when we react oxygen with LP gas, the C3H8 called as propane to 5 oxygens. It produces carbon dioxide plus H2O plus the energy. And please write this down. LP is converted into LP reacts with oxygen, right? Please write this down under the energy changes in chemical reactions. And in this second example, I wrote down what happened when this is actually the photosynthesis. This is the photosynthesis reaction is explained in here. So in a tree, the sunlight and tree actually absorb carbon dioxide and water, and under the photosynthesis process, they are trees are producing oxygens and other carbonic groups. And you can write down this one as well. You can write down as photosynthesis process. So now I believe you write down this one as well. Again, you can write down uh, all chemical reactions, all chemical reactions all chemical reactions absorb or produce energy. Absorb or produce energy. Under the produced, after the produce, you can, under the bracket, you can write down release. Okay. Produce means again the same meaning, release. Absorb or produce, in the bracket, release energy. Generally in the form of heat. In the form of heat. Now, so I'm going to repeat the same thing. All chemical reactions absorb or produce, under the bracket, release energy, generally in the form of heat. Now, again, you can write down in the next point, heat is the transfer of thermal energy. Heat is the transfer of thermal energy. Heat is transfer of thermal energy between two bodies. Between two bodies. Between two bodies that are at different temperatures. So if I repeat that one again, heat is the transfer of thermal energy between two bodies that are at different temperatures. Okay. So I'm going to explain that one for you. So now we know what is the temperature, right? What is known by the temperature, we know it is the mean value of kinetic energy inside the object, right? The kinetic energy of the object's atoms. Now, what about heat? heat is actually, if I take two bodies here, so here again, I take two objects. Okay, I take two objects with different temperatures. Let's say this green object is in 150 Celsius. It is in 150 Celsius. Okay, but the red one is in 80 Celsius. Now, if I ask from where to where the heat is going to be transferred, from where to where, actually, uh, uh, you know, when what is your guess? What's your best guess? The heat, or we called as tape. Tape කොහෙ ඉඳලා කොහෙටද ගලාගෙන යන්නේ. එතන උෂ්ණත්වය නිසා ඔයාලට පේන්න තියෙනවා, you can see the temperature difference, but which way the heat is going to flow? Is it from the least one to the maximum one, or from maximum one to the least one? So generally, this is a common practice. We know where the water is actually flowing from the highest position to the lowest point, right? The water is flowing from the highest position to the lowest one. So actually, the flowing of water is also like the heat. Heat flow is also like the water flow, which means from highest temperature to the lowest temperature, the heat is going to be transferred in this direction. Okay, in this direction, it is going to be transferred. Now, now if I ask a question like this, okay, now you know the heat flow is actually from highest temperature to the lowest temperature. Okay, now if I ask a question, there's another object here again. Another object is like this. Let's say it is also in the 80s temperature. Now, from where to where this the heat is going to flow? If I consider only two objects, the red one and the orange one, in which side is it, from red to orange or orange to the red? You can use the chat box for an answer. Again, I am asking, if I consider these two squares, these two objects, from where to where the heat transfer is going to be occur? That's my question. So you can write down either as orange to the red or red to the orange. I hope you can see the change in these colors. Okay, both of them are in the same temperature. Yes, your answer is correct. There's no heat will transfer in between these two bodies. Why? In order to, if in order to flow, in order to have a heat flow, there should be a temperature change, right? So if it, both of them have the same temperature, which means there is not no flow, right? So you are correct in that point as well. I think you are really good at these things when it comes to heat, uh, because most of the guys, they don't understand heat because it's in the very beginning. So now if I come to some practical aspects, so let's see that so in this one, I mean, you can see in everywhere we are absorbing heat or we are releasing heat, you know. So if we have so when we have like a sunburn, why we have sunburns? Due to the excessive sunlight, what happened is the heat is going to be the, you know, from the sun, it has a higher temperature, but in earth's, our skin has like room temperatures or body temperature, like that, you know. So from transferring heat from, so due to this difference in temperatures, we are going to absorb the heat, right? We are going to absorb the heat, and from the sun's aspect, the sun is going to produce the energy, or it is going to release the heat, right? It is going to be released the heat. It is going to let's see, so the same concept if I apply it to here, if I can write down this 150 object, let's say this is the object A and this is the object B. The A is what? A is actually what he is going to release the energy, right? I can draw a much more proper appropriate way today, I think. Then I think A is producing energy or releasing. So here the A is the one who produce energy and B is the one which is absorbing energy. So let's see, so consider this B is our hand for a moment. Just consider B is our hand, okay? Now for the 151, consider boiling water. Consider boiling water. So what happened when boiling water touches our skin or our hand? What happened? Due to our lowest temperature, there is going to be a heat flow conducting through our skin, right? That's why we feel the pain, right? We get the burning sensation, right? right away. So what in the, however, so you can see the B is going to be heated up, right? Because it is the one who absorbs the energy. A is the one who is releasing energy, or he's producing energy. You can use this. I mean, the release energy means the release energy is more appropriate in here, right? Rather than producing energy, I mean. So again, for another example, if you take an ice cube onto your hand, now actually the B should be your ice, right? B should be your ice because it has the minus temperature, right? And in our hand, what happened? It has like body temperature like 30 Celsius, right? 30 Celsius, likewise 27 Celsius, like that. But ice cube has a minus temperature. So what happened? Our hand is going to be the one, or the ice cube is going to be what? The ice is going to be absorb energy, right? The ice cube is going to be the one who absorb the energy. Then our hand is going to release energy. In that case, what our sensation? We feel the like a cool sensation, right? Rather than in a burning one. I think you get the point in here. You can draw this diagram, and you can write down this. The last one has C as well. The last one has C as well. Then you can write down B, and there are no heat transfer between B and C due to zero temperature change, like that. Please do write and let me know when you finished. Please ask any question. Do I have to repeat myself? I'll type it in here so you can easily write down this one as well. Right, now you can write down. So again, another point you can write down. We often speak of the heat flow. We often speak of the heat flow from a hot object to a cold one. From a hot object to a cold one. Although the term heat by itself implies the transfer of energy. Implies the transfer of energy. Thus, we often speak of the heat flow from a hot object to a cold one, although the term heat by itself implies the transfer of energy. We customarily talk of heat absorbed or heat released. Customarily talk of heat absorbed or heat released. Heat absorbed or heat released when describing the energy changes. When describing the energy changes. So rather than we are talking about like heat flow, we just say either heat absorbed or heat released. So I think now you have the potential to understand whether which one has released the heat and which one is going to be the absorb the heat. So it depends on the temperature, right? Temperature, the least temperature guy is going to absorb the heat, and the highest temperature guy is always going to release the heat or produce the heat, right? And so now we come to the main topic. So do you want me to repeat that one again? So again, I'm going to repeat that one. Thus, we often speak of the heat flow from a hot object to a cold one. Stop, full stop. Although the term heat by itself implies the transfer of energy, we customarily talk of heat absorbed or heat released when describing the energy changes, right? Now you can write down the next point. Thermochemistry is the study of heat change in chemical reactions. Thermochemistry is the study of heat change in chemical reactions. Now here are some terms you have to use under the thermochemistry. They are commonly used in a question, so you can easily understand. I think in the previous question, I'll show you the previous question again. Here it says that yeah, you can see the system, the word system in here, and you can see the word surroundings in here. So likewise, these are some terms described in this under the thermochemistry. They're really simple. So I'm going to again change to the whiteboard. So under the thermochemistry, you can write down. First one point system. Under the system, you can write down system or the specific part of the universe, system or the specific part of the universe, system or the specific part of the universe that is of interest to us, that is of the specific part of the universe that is of interest to us. So under the second topic, you can write down the surroundings. The second one, surrounding. I'll explain them in a detailed manner. Please write down surroundings. Under surroundings, you can write down surroundings are the rest of the universe outside the system. Surroundings are the rest of the universe outside the system. And so surroundings are the rest of the universe outside the system. And so if I draw these things first, so consider a fish tank. The simplest example, consider a fish tank. So here you can see the fish tank. Just consider, so if the interest, I mean to my interest from the universe is, it is going to be the fish tank in here. Okay, so in that case the system is defined as the, I mean, in the universe that is of interest to us or interest to me, so it's going to be the fish tank. So I write down, then I will say my system is going to be the fish tank. So my system is going to be the fish tank. And what about the surrounding then? What about the surrounding? The well, surrounding, they say that, what is that? They say the surrounding is, are the rest of the universe outside the system. So all the other things in the universe called as my surrounding. So I'm going to write down here, this is my system here, it is my interest, and all the other part is called as the surrounding in the universe. So now I can simply now tell me, is it true or not? So if I add system to the surrounding, if I add my system plus the surrounding, it's going to give me the universe, right? Well, it should be true, right? If I add my system to the surrounding, it's going to give the universe. So like that, surrounding means any other things. I mean, for example, any people, any house, anything. Even the sunlight coming from to the water tank, any water coming to the water tank, other everything is called as surrounding. Then when we talk about the boundary is the it's the, here you can see the boundaries here, this one, right? This is my boundary, the limit where it separate system and surrounding. So it is the limit that separate system and the surroundings. In that case, I have to take what if I consider this whole fish tank, then it is the imaginary line of system and surrounding. It should be imaginary line along this line. But if I only consider the water in here, if I only consider the water in this water and the fish, then the glass tank is going to be my boundary here. So boundary depend on our expectations. Okay. So this is a quite a simple explanation, but in thermochemistry, we usually undergo many reactions. In that case, I'll provide you with a proper one. And here, if one consider for an example, so let's take a glass tube like this and put any kind of solution solution here. Let's say sodium hydroxide solution or HCl. HCl called as hydrochloric acid. NaOH means sodium hydroxide, right? So I can use there should be a a glass tube or the experimental tube here and filled with HCl, and we can say this is my system now, and anything happen from outside it is going to be my surrounding, right? Now my boundary is the beaker wall or the experimental tube wall here, and if you I think it is better to do like typical example. You can write like this. So this one is my system. There may be, this must be anything, and all the other things known as surrounding, and the limit which separate these two called as the boundary. So at the same time, I think you can write down this one, system plus surrounding equal give us the universe again. And I think it's better to draw this one, surrounding, boundary, and system. Please let me know once you finished. Now, again, there are actually three types of systems we have to learn about. So under the, again, you can write down the topic system and subtopic. First one is the open system. First one is the open system. So again, under the first one, open system, please write down. Open system can exchange mass and energy. That's it. Open system can exchange mass and energy. Mass means the scan there. Oh, So here again, can exchange mass and energy. Example, you can write down an open system. Sorry. For example, you can write down quantity of water in an open container. Water in an open container. Water in an open container. And for the second one, you can write down closed system, open system and closed system. Under the closed system, you can write down which allows the transfer of energy, which allows the transfer of energy which allows the transfer of energy but not mass, which allows the transfer of energy but not mass. Okay, but not mass. It can be used to exchange energy but not mass. Then the last, for example, for that one, you can write, for the example, you can write down placing the water in a totally insulated container. Sorry, no, that is not the example. Close the water in an open container. Close the open container which has water. Close the container which has water so that no water vapor can escape. No water vapor can escape from. No water vapor can escape from or condense into the container. Condense into the container. Right. Now you can write down again. Right. Right. Okay. Sorry for the inconvenience. So under the then you can write down the. Do I have to repeat the same sentence? Or otherwise, I'm going to do the isolated system. You can write down the isolated system, and under the isolated system, you can write down which does not allow the transfer of 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 either mass or energy. Either mass or energy. Either mass or energy. Which does not allow the transfer of either mass or energy. For example, you can write down by placing the water in a totally insulated container. By placing the water in a totally insulated container. Now, so I will show you a figure for that. I will share the screen again. So I think, can you see the screen? Yeah, I hope so. So this one you can see the water container, and the figure A represent the open system, right? So in that case, mass means විතර මාස් එක කියලා කිය මාස් එක කියලා කියන්නේ ස්කන්ධය කියන්නේ මේක ඇතුලේ තියෙන ඕනම දෙයක් මේක ඇතුලේ තියෙන ඕනම ස්කන්ධයක් තියෙන ඕනම දෙයක් එළියට යන්න පුළුවන් නම් සහ ඇතුලට එන්න පුළුවන් නම් මගේ senses I consider this water bottle as my system. Okay, this water container as system. Actually, this one is an open container. So the mass can be exchanged, right? And at the same time, what happened? The heat can also heat or any kind of energy. Any kind of energy can be transported in or absorbed for produce energy. So if the sunlight is a kind of energy, that radiant energy is going to inside of this water, right? So energy is transferred here. And likewise, this is called as an open system. For example, a cup of tea without any lid on top, right? And for closed system, you can see now the mass cannot be changed. Now, if you turn over the bottle, you cannot, get this water out the side, right? Even the water vapor cannot escape from this knob, right? So this is a closed container or the closed system, but however, still heat can be exchanged. So if I take a lighter and if I put this one on fire, the heat is going to be, or that heat energy is going to be transported into this water. And for the last one, this is our isolated system. So this is insulated. This is fully insulated. This is fully insulated. In that case, there is no heat or any kind of energy is going inside or the inside energy to the outside. At the same time, there we cannot get in or get out water out of this. So no mass transfer as well. So this one is called as our isolated system. So for example, you can see an open system which allows the exchange of both energy and mass with surrounding. The B1, a closed system which allows the exchange of energy but not mass. And the third one, isolated system, which allows neither energy nor mass to exchange. Here, for example, we can you can I can the in day to day, what is the isolated system with the best one we use? I cannot remember the name in English, but I think it's called as you know how we call that, the hot water flask or something, hot water container. Actually, hot water container is a isolated system, right? Hot water container or the water flask is the so hot water flask is for like when you put hot water there, the energy, the heat or the temperature or the kinematic energy is not transferred to the outside. That's why it is also always keeping the heat inside. After a long time, it is not going to be, drop the temperature, but it is going to be a constant temperature. So in the same time, if I take like ice cubes and put it on a vacuum flask, right? If I take a vacuum flask and if I put ice cubes inside there, then I'm going to close the flask, and after 5 or 6 hours or 3 or 4 hours, what do you think what happened? There are two possibilities. Okay, you can answer as the first one. First one means the ice is going to be melted away, right? Ice is going to be melted away. Now my second option is, I say ice is going to stay in the same state like we put in there, the original position, original state. So these are the two options, 1 and 2. So what do you think? In a vacuum flask, if you place some ice cubes, what is going to be your answer? Is it going to deform or is it in on the original state? So do you have any answer? Or didn't you get the point in here? So actually,
So the first,
please use the chat box. I can't actually hear you. I mean, the surrounding sound is large. Can you hear me? Uh, well, yeah. I mean, actually, the ice is going to stay in its original position. Okay, ice is not going to melt in a vacuum flask. But let's see. I mean, if you put like hot water there, it is going to stay in the hot water state after some time. So that happened because there is no uh, heat exchange with the surrounding with the system. So same thing applied to the ice cubes as well. So ice cube, ice cube. What happened? Ice cube try to absorb energy, so it can be melted down. But what happened is, since there is no heat exchange without outside or the surrounding, it is not going to melt at the way. It's I mean it's presented in the original state as ice cubes. So you can write your own that one. And so if I ask some question, I think I can find you another question from this one as well. Just give me a second here. I will find the exam question for you. I think I have a quick question for you. So this is one from 2018. So the heat can be defined as what? What do you think? There are 5 choices here. Is it a temperature of? I think you can see the screen, right? Yeah. Heat can be defined as the. What do you think? Temperature of a system, flow of energy between two systems, amount of work done on a system. It's okay whether you got the wrong one. It's totally okay. The third one, yeah, that's exactly the correct one. So, did you do any? I mean, did you do any physics? Or did you participate for physics or any classes? So you just do the. I mean, for the SFT for the first time, right? So heat is actually the flow of energy between two systems. It's the flow of the energy. That's the point in here. So like that's so I want to talk about this pressure as well. I think I would remember the point in here. Let me properly take for that. Okay. Right. That's the system. I think I'm having hard time finding the question. Yeah. Yes. Okay. That's very unfortunate. So I want to get you familiar with this question. So this ability is not hard, you know. It's a very easy one. There's a question. To go back to the length or something. Yeah, this is the problem. Now I want your answer. I finally find the question. So based on matter and energy exchange, here the matter means the mass, okay? Matter and energy exchange. With type of a system, a cup of hot water without a lid can be classified into. I will zoom it for you. you can give me answer. You just learn about there are three types of systems, That should under which category the answer should be there. Like which one? Is it open? Is it closed? Is it isolated? Yeah, open system, right? The most probably, I mean, the 2006 guys, they forgot about this without the lid. Man, I mean, without the lid, they just forget about this word. So here it is actually open system, but in the figure you can see this is kind of a hot coffee making machine. Here under the, I mean, the bottom of the part, they are using a chamber to put some chemicals, and they are get the reactions here. And since it is an exothermic reaction, the coffee cup is going to be heated by itself. It's kind of a new invention. And here there's a lid. Okay, so the question is, but in bottom of the, I mean, it's the nearest point we can find, right? So when it comes to which type of system, if you just look at the uh, answer, you might say this one is a closed system because there's a lid here, right? So you have to be careful with this. I mean, it's in A level, it's a word game. It's completely a word game. So without lid, it's an open system. That's correct. And right. Okay. So I believe we do some introductions in here, and I think it's time to stop the lecture for today. I will start with this endothermic and exothermic reactions in the next week. So probably if you have any questions, please let me know. So we are just covered a single part, so you can see the from the basic things. Actually, they were asked questions in A level. So what happened is, if you go through this lesson in the, I mean, for the bottom of the side, I mean, at finally what happen is you are actually good with that. I mean, hard questions you are good with that, all of them. But I mean, after 2 years, you forget about the basic things. But you already see that there are lots of basic questions in the A level from these things, right? So if you get the basics right, then advanced and intermediate, that's a piece of cake. So you didn't have to worry about these things. If I will brief you what we have talked about here, we talked about systems, surroundings, and the boundary. And under the systems, we talk about three points: open, closed, and isolated system. They differ on the mass and energy exchange. Previously, we talk about heat, which is actually transfer of thermal energy between two bodies. And we actually, in order to transfer thermal energy or the heat between two bodies, we have to have a temperature difference. Otherwise, it is not going to transfer the heat. And in the same time, in the morning introduction, we talk about energy. There are lots of energy. And when we come to the rules of the golden rules of energy, or the known as the law of conservation of energy, they say all forms of energy can be converted into another form, and energy can be neither destroyed nor created, and the total quantity of energy in the universe is assumed to be constant. And mechanical energy means kinematic and potential energy. I will come to the equation of these as well. So there are equation for these two. So probably we can do the in the next week we can cover up that parts. Then likewise, if you don't have any questions, I'm going to end the lecture for today. I'll give you like 1 minute. If you have any questions, please let me know. If there are any comments, please use the chat box for that. So thank you for your participation. If there are any inconvenience with the audio, I'm sorry for that. Right. Okay.